property called the Van Zittel-Zernike theorem, which allows you to calculate the coherence function if you know the shape of an incoherent source. So here the assumption is that the LED is spatially incoherent within this aperture. Then what you do, it turns out to be yet another Fourier transform, and then from that you can calculate what is the coherence function at some distance, and it's supposed to look like this. This is a one-dimensional field, so the coherence function has two dimensions, x1, x2, and that's what it's supposed to be. Right. So this is our truth. This is what we hope that the experiment should recover. Is it going to be like this or not? So as I mentioned before, the experiment is limited because we do not have the full data. We only have access to 2/3 of the, rather 1/3. We have access only to 1/3 of the measurement space. So, and this sort of number is called the global degree of coherence, and it is one more way to characterize this kind of function. So let's see what you recover if you use standard tomography. In standard tomography, the approach that they use in medical tomography, security related and so on, the standard algorithm is called filtered back projection, and it gives you this. So this does not look at all like the ideal reconstruction. In fact, it looks very wrong for two reasons. The obvious one, that if you calculate the degree of coherence, it is 0.12, whereas the true value, as I mentioned before, it is 0.49. The second problem is that it's supposed to be a correlation function. Correlation functions, when the two arguments are equal, they're supposed to peak, right? Every correlation function must have this property. But this one does not. If you look carefully along the diagonal of this matrix, it is not a peak. It actually has a dip. So therefore, this result is very seriously wrong. And of course, it is very seriously wrong because of the missing data in the measurement space. Okay, so what you see here now is a reconstruction using the L1 metric. And you can see that it actually has recovered both problems. The degree of coherence is much closer to the true value. We estimate 0.46, the true value is 0.49. And most importantly, this is now a physically correct correlation function. It peaks at the diagonal of the matrix. I think I ran out of time, so I will show very briefly, I will show you a few more things and then I will stop. So first of all, we calculated the error between the true correlation function and the recovered one, and you can see it is very small here. It is 0.02. The peak here was at least a factor of 10 higher, so we're doing quite well. Except for these edges here, the error is actually quite high, and that is because of edge effects. So okay, it is not perfect, but at least it is doing well in the center of the space here. Okay, now the second thing I want to show you is a few calculations of, you can think of those as the eigenfunctions of this system. And this actually explains why this technique works well. If you calculate this, these are the eigenfunctions, we'll call them coherent modes in optics. If you calculate the eigenvalues, you see that very few of them are non-zero. Up to here, then the rest of them are zero. So this is why this technique is working. Even though the measurement space is highly undersampled, nevertheless, it is a sparse measurement because very few eigenvalues are zero. So what we did actually in order to make it work, you can see the details in our paper, but what we did is basically we translated this physical property into a mathematical requirement, and then we applied the L1 metric on it. That is the basic idea. And then what you see here is the true values. Again, you can see it agrees very well with the previous one, and then this is the error. So you see it is quite small. And this is what these coherent modes look like. They look kind of pretty. So that's why I'm showing them. They have interesting physical significance. I do not have time to go into it. And again, you can see that if you compare the true modes to the estimated modes, again, you can see that the agreement is quite good. And then the last thing I want to say is that we've also done, this was a one-dimensional measurement with a two-dimensional coherence function, and then we did a two-dimensional measurement with a four-dimensional coherence function. Okay, so in this case, the experiment is a little bit more elaborate. you do something that this guy is discussed in this paper over here, Mark, Stack and Brady 2000, in order to do this measurement properly, you have to insert in a stigmatic system 2 cylindrical lenses crossed, and then you have to scan both those 2 stages. You have to scan the camera. This is sort of the basic idea. That's how you take measurements downstream the optical axis. But you also have to scan the stage, it turns out. Because again, here we're trying to recover a higher dimensional space, so you would expect that you have to take more measurements. That's why we need this additional scanning requirement. And then this is what we measure. Now this is a 4-dimensional space, so I cannot quite show it. This is kind of rastered here. So each one of those dots corresponds to a pair of x1, q1 variables, and then the big one is the x2, u2. That's one way to visualize a 4-dimensional space. And then you can see that we have very drastic limitation. All of these data are missing for each one of these measurements. But nevertheless, we recover the true coherence. So this is the true coherence function, what we should recover, and these are the eigenfunctions. And then this is the reconstruction, and you can see it looks quite similar. This is the eigenvalues, and this is the eigenfunctions. Okay, so I've run out of time. So I was planning to talk a little bit about X-rays, but I didn't have time. So unfortunately, I have to stop here. It is an excuse for Jalum to invite me to come back again. And I think that the last slide I will put up some references here that, and I can give you a copy of that if you would like to look further. Thank you for your attention.
We have time maybe for 1 or 2 questions. Any questions?
I'm not familiar with this Wigner distribution. How sensitive your result to noise?
Right, that's a very good question. This is always the problem in inverse problems, right? So if the sparsity assumption is true, so if the coherence function is indeed sparse, it turns out it is surprisingly robust to noise. And that is because the noise is not sparse, but the measurement is sparse. So the algorithm actually kills the non-sparse part of the signal. That is one of the strengths of this technique. Of course, there's limits even to that, but it is actually quite robust, much more robust than the standard regularizers. Yeah.
Any other questions?
Yes.
Is there any imaging applications that the compressive reconstruction is applied to?
Yeah, well, since you gave me the excuse, I will show you one. As it turns out, I will not show you the details, but I will show you an example of an experiment that we did. So what you see here, this is actually the mouth of a beetle, the insect. And we image that using X-ray phase imaging and compressive sensing. So this is, even though here we do not use the phase space approach, the ultimate way to do this kind of measurement would be with phase space. And of course the beetle itself is not very interesting, but there is this is just a demonstration, but there's 2 very important applications. One of them is of course medical imaging, where X-ray phase, it turns out, can give you faster diagnosis, so you can basically catch cancer much sooner. And the second is for security imaging at places like airports, you know, luggage screen and so on, where phase-sensitive X-rays, they give you better discrimination between forbidden substances and allowed substances. So these are examples where all of these techniques come together and work. But as I said, in this case, we did not actually reconstruct the phase space. We simply reconstructed the optical path length. Yeah.
If the object is also absorptive, it's complex, then how good is this?
Very good question again. So you're right. One way to do it is to simply assume that the absorption is small, and then of course the technique gives you a correct answer. If the absorption assumption is not true, if the absorption is significant, these techniques they produce artifacts. We have just started working on this problem, and we have some ideas for how to reduce the artifacts. It is not an easy problem, right? Because it reduces your signal, and at the extreme, if the absorption is very high, the phase information completely disappears, and worse, if the intensity goes to 0, then you get a phase vortex around this point, right? Then you have a serious problem. Okay, in reality, in real objects, at least in medical imaging, you would get a phase vortex if you image bone, obviously, but if you image soft tissue, so you limit your field of view, that you look at soft tissue alone, then you do not have this problem. On the other hand, if there is mild calcification, if the patient is at the onset of cancer or atherosclerosis, anything that produces calcification, you will actually see it. So it is actually quite beneficial. We have not completely figured it out, but there is ways around it. One way, for example, that we use, I will reveal to you our secret, is we use attenuation phase duality. In X-rays, the attenuation and the phase are correlated, right? So you can actually use it as a prior. That's one way to deal with the problem. But as I said, we're still working on that.
Okay, due to the limited time, let's end the lecture now. If you have more questions, please come to the front and talk to the speaker. Let's thank the speaker again.
Thank you.